Hi, my name is Amy. I'm a research scientist at Apple and a postdoc at CMU. Today I'll present Rescribe, a tool for authoring and automatically editing audio descriptions. I created Rescribe at Apple with my collaborators in the machine intelligence group, Gabriel, Reyes, and Bigham. Online videos such as how-to tutorials, travel guides, and product reviews provide information both auditorially and visually. But the visual content in videos can be inaccessible to blind and visually impaired audience members. This creates unnecessary barriers to accessing information. To make videos accessible, professionals create audio descriptions, or narrations of important visual content that avoid overlapping important audio content. Professionals often omit visual content or offset the timing of their narrations to make everything fit. Here's an example.
What role will you play? Who will be the future of Mount Rainier National Park?
Job titles appear including trail crew, archaeologist, engineer, climbing ranger, and more. Future rangers. Children wear uniforms for different park jobs. Linnea.
I'm a future archaeologist.
Here, the author omitted details like Linnea's safety vest and offset the timing of their descriptions. We interviewed 7 audio description professionals, including producers, audio engineers, script writers, and teachers, to learn how to create audio descriptions. Professionals outlined the following steps. First, they identify gaps in speech and note the start and end timestamps for each audio gap. Next, they describe the important visual content in the video. For instance, at 21 seconds, Linnea, the park archaeologist in 2033, wears an orange safety vest. Each of these descriptions takes time to say. So our initial descriptions might overlap with each other and the source video speech, such that they don't fit within the audio gaps provided. To make the descriptions fit, authors must edit the description timing, delete descriptions, or shorten description text. This iterative process is tedious and time-consuming, taking hours beyond the initial draft. Our goal is to let audio description experts and novices describe videos efficiently. To facilitate this, we'll let authors identify and describe all of the important visual content. Then, we'll automatically optimize descriptions to fit by jointly shortening text and lengthening the source audio. Lengthening the source audio allows a new type of audio description that I'll talk a little bit more about later. Using our tool Rescribe, authors can input their source video, then visualize the speech and music or silence gaps along the timeline. Rescribe also transcribes the speech from the source video and visualizes the gaps in the transcript. Authors can navigate to gaps using the transcript or timeline. So here an author navigates to 2 timeline gaps. Authors then script their descriptions by playing and pausing the video. Here an author types title, Gabby's Guide to Ojai, What's Gabby Cooking? And then a montage of bright footage from Ojai. The interface interactively updates the timeline and transcript to show authors an approximation of the remaining time. Authors then record their descriptions.
Shots of lavender in a farmer's market. Red flowers against a white house and blue sky.
Authors can click Create Audio Descriptions to render their descriptions. Rescribe automatically edits the descriptions to fit, and authors can listen to the result.
Title, Gabby's Guide to Ojai. A montage from Ojai. Shots in a farmer's market. Red flowers. A courtyard and a pool. Gabby bikes along a path. Close-up of French fries. Gabby drinks sangria. Gabby and Thomas sit on a couch.
Hey guys, Gabby's Guide to Ojai is coming your way.
Authors can then change the descriptions without re-recording by editing the text or locking a description. Rescribe can render 3 types of audio descriptions: extended descriptions that play back the full descriptions by pausing the underlying audio. Inline descriptions, as we listened to earlier, these play alongside the audio by shortening the description text. For instance, Rescribe shortened red flowers against a white house and blue sky to just red flowers. Rescribe can also render a new type of audio descriptions called extended inline descriptions. These descriptions subtly loop the underlying audio to fit more of the original description text. This one breaks the sync with the video, so I'm just going to play back the audio.
Title, Gabby's Guide to Ojai. A montage from Ojai. Shots of lavender in a farmer's market. Red flowers against a white house and blue sky. A courtyard and a pool. Gabby bikes along a path. Close-up of tater tots and French fries. Gabby drinks sangria. Gabby and Thomas sit on a couch.
Hey guys, Gabi's Guide to Ojai is coming your way.
So this is the first video guide for Gabi's Guides. So we're going to take you through.
Next, I'll share a few of the algorithmic methods that power Rescribe. First, Rescribe identifies speech, silence, and music in the input video by transcribing the video and then classifying the non-speech sound. Next, users script and record their description. Rescribe finds an alignment between each scripted description and its recording. Finally, Rescribe edits the description using one of four methods. So it either edits the content of the description by shortening or deleting the description, or the placement by adjusting or extending the source track. We'll talk a little bit more about how we edit descriptions. So first, for each user-generated descriptions, we create a set of candidate descriptions for inclusion in the final track. Our first description candidate is just the original description. So here, we'll just have Gabby and Thomas are back on the couch in their sunny living room. From there, we can remove adjectives and adverbs like sunny, or prepositional phrases like on the couch to get Gabby and Thomas are back in their living room. Finally, we can remove members of lists and compound clauses. So here I'll remove and Thomas to get Gabby are back, which doesn't make sense now, but we'll get back to it later. And then finally, we can delete descriptions. So in total, we'll have 200 to 300 plus candidates per each description, considering all possible edit combinations. To select which one of these candidates will be included in the final descriptions, we then need to score the candidates. In particular, we consider informativeness, coherence, edit quality, and placement of each candidate. So informativeness seeks to preserve phrases and words that will be important to the rest of the description and the video. Here, Gabby and Thomas get a point because they are used in other descriptions. Gabby later talks about the living room in her source video script, so the living room also gets points. We'll give half points for nouns and verbs, which are used more commonly in expert descriptions than adverbs and adjectives, which are used more commonly in novice descriptions. So the original script descriptions here scores the highest, but the second description is pretty close, but it's a little bit shorter. We generated our candidates via simple rules to control the space of possible candidate descriptions. But a common problem with rule-based approaches is that they can be fragile and generate grammatically incorrect results like Gabby are back. So we use a robust language model, GPT-2, to find the likelihood of a sentence occurring in English. Generally, most scores for each description are close to each other, but grammatically incorrect sentences are often orders of magnitude less coherent than the others. Our edit quality metric acknowledges that each edit we make to the original speech based on the text can introduce disfluencies from misalignment and intonation changes. We assign a penalty to each cut. So the original sentence doesn't require any edits, and it doesn't get a penalty.
Gabby and Thomas are back on the couch in their sunny living room.
The second candidate requires 4 cuts, 2 to edit out on the couch and 2 to edit out sunny.
Gabby and Thomas are back in their living room.
So that receives a penalty of -4, but it still sounds pretty good. The third candidate requires 3 cuts, 2 to remove and Thomas, and 1 to remove the rest of the sentence. Any cut that removes the end of a sentence receives a higher penalty of 3 instead of 1, as the last word of the sentence often contains a distinctive downward intonation.
Gabby are back.
So we can hear back kind of cut off there. So these scores only consider the candidate descriptions themselves, but we also need to score the placement of these descriptions in the video timeline. If the video timeline includes only speech, all descriptions will get a high penalty when placed at their starting time. If a gap's available, they'll receive no penalty. If a candidate overlaps with an existing description, it again receives a super high penalty. We can move descriptions from their starting point at a rate of -1 per second. So now 2 of our descriptions we've moved 3 seconds are at -3, but one's still at -infinity because it still overlaps with the speech. Finally, if we extend the source track to fit a candidate, we assign a penalty at a rate of -1 per second extended if an extension is possible. So now all candidates have a penalty of -6 for a 3-second adjustment and a 3-second extension. Using these scores, we can define our objective function. So for each description, DI, we aim to find a candidate J and a placement time T to maximize the sum over all of the descriptions from D0 to Dn, where n is the number of descriptions. Given our constraints of maintaining description order and including at most 1 candidate per description, we can formulate this as an optimization problem to maximize our objective function. So we find the optimal solution of candidates and times for each description using dynamic programming. And the paper includes more details. We evaluated Rescribe with 3 user groups: novice audio describers, blind and visually impaired audience members, and expert audio describers. Novice audio describers overlapped 45% of their descriptions with speech or other descriptions when using a traditional editor. We cut these errors to 0% when they used Rescribe. Surprisingly, novices found gaps in a similar amount of time using both Rescribe and the traditional interface, but they preferred Rescribe for drafting the descriptions anyway. Instead, some of the participants just wrote too many descriptions in both interfaces, and those participants preferred their Rescribe-generated descriptions. Blind and visually impaired audience members, comparing our 3 types of audio descriptions, preferred the Rescribe-edited descriptions over the original extended descriptions that had to pause the audio. Participants also preferred extended inline to inline descriptions, particularly for viewing without sighted people because it breaks the video audio sync. They like the ability to have more information without breaking the tone of the video. Finally, we demonstrated Rescribe to experts. Initially skeptical, experts liked that Rescribe let them write their own descriptions and then only automated the tedious parts of their job. They wanted to use Rescribe in their workflow and suggested improvements such as automatically applying descriptions for objects they had previously described. Our work contributes to automated media editing and video accessibility. Prior work has automatically edited video or audio to fit speech of narrated videos and scripted videos, interview videos, and audio stories. Rescribe uniquely automatically edits the speech to fit the audio or video by using a combination of rules, scoring, and robust language modeling to achieve high-quality results. And outside of accessibility, Rescribe could be used for applications like creating voiceovers when you only have a limited amount of time. We built Rescribe by considering existing description guidelines and captioning tools that are kind of confusingly already used by experts to create descriptions. We also analyzed novice descriptions on udescribe.com to inform our work, finding that 50% of descriptions paused the underlying video even when they didn't need to. Finally, a few special purpose audio description tools let users synthesize speech from text, but description audiences still prefer human narrated descriptions. So we're the first of the video accessibility work to use computational support for description editing. And through this support, we introduced a new type of descriptions, which are our extended inline descriptions. Our work opens up a few new research opportunities. So first, audio descriptions make videos accessible after the fact, but in the future, we could instead provide video authors feedback on what objects or actions they have not yet described. Second, for many types of searches, there might exist multiple viable videos, and different videos have different levels of accessibility. For instance, 2 videos about a paper airplane, one that's fully described is going to be more accessible than one that's just a montage of different paper airplane techniques. So in the future, we could compare the audio and visual content to surface the videos that are likely to be more accessible. And then finally, audio describers mentioned an additional challenge that we didn't address with this work. How do you describe a video when you don't have domain expertise? So audio describers mentioned this challenge, particularly in describing like a video game or a cricket match in part of a larger project. Future research could explore how to surface vocabulary or prior descriptions for objects and actions to assist describers. Improving our domain-specific descriptions could also improve training data for describing videos more generally. So I would like to thank all of my collaborators on the MI Accessibility Research Group at Apple. And if you have any questions, don't hesitate to get in touch. Thanks.